So focus on this problem here, we're given a vector field and we want to compute the outward flux on this. So we're going to assume, so our surface is a sort of box that encloses a rectangular prism. So one quick thing on this notation here, you'll see this notation sometimes. This notation is equivalent to this notation, which is more common, and that's the notation that our textbook uses. But I wanted you to see this notation as well, since you'll see that in other text. So what I'd like to do is first make sure that we understand the problem. So let's go ahead and sketch our region first. And then our region is oriented so that we consider the normal vectors to this to be outward facing or outward pointing. So let me just sketch a few of those. I'll put the outward normal vectors in red. So now we imagine this vector field that sort of permeates throughout this space. And in this case, we are, for every vector that sits on the surface here, maybe we have some going inwards too, we're going to compute the dot product of the normal vector with the vector in the vector field. That's a measurement of the flux throughout. If we wanted to tackle this problem directly, we would have to compute the flux on the surface of each of the 6 faces of this cube. So we'd have to break it up into 6 separate flux across the surface problems. The easier way to tackle this problem is to utilize the divergence theorem. And one hint that we may want to try the divergence theorem is the fact that this is a surface that's completely enclosing this box, all 6 sides, and so that encloses a region. And the divergence theorem tells us that when we have a surface that completely encloses a region, we can instead compute the divergence throughout the region, and that gives us the flux across the surface. So let me just state that divergence theorem. And I think the thing to keep in mind with that divergence theorem that could sometimes get you in trouble is that we require that the surface completely enclose E. If your surface doesn't entirely enclose a region, then you can't use the divergence theorem on it. So as our integrand, we're going to need to compute del dot F. So let's go ahead and do so. Now that we've computed the divergence, let's go ahead and write out our triple integral as an iterated integral. Because the region for this iterated integral is a parallelepiped, there's no reason to favor one choice of order of integration over the other. I just happen to choose dz, dy, dx for integrating. There's no reason why you couldn't have interchanged those. Let's now compute that integral. And so we find that the divergence throughout the solid region, the solid rectangular prism, is 12. That is, if you summed up the sinkiness or sourciness at all of the points inside this solid parallelepiped, that would be computing this expression. But the divergence theorem tells us that computing that expression is equivalent to finding the flux across the surface that encloses that region. And so we've answered the question, finding that the solution to that integral is 12.